This week on Thinking Deeply About Primary Education.
That's like much more than just being able to recite a definition. It's about the connections between the ideas.
And in a primary setting, I believe that the concrete and the abstract should go hand in hand.
What you've done there is sort of highlight the depth to which your expert edit goes in terms of making connections.
If abstract symbols are introduced too soon, pupils may struggle to grasp their meaning, while remaining at the concrete stage for too long may hinder their ability to analyse and apply knowledge flexibly.
The reason we've got those abstract symbols in maths is because they're efficient and they can be transferred to lots of different situations. But to do that requires that kind of conceptual understanding underneath it all.
Welcome to Thinking Deeply About Primary Education, the podcast that makes time and space to think about pedagogy, teaching and learning, professional development, anything of interest to time-poor but enthusiasm-rich primary teachers. This week, I'm joined by Emma Lindley-Thompson.
Hello. Hi, Kieran. Hi, everybody.
And John Jackson.
Hi, Kieran. Hi, everyone.
It is fantastic to have you guys back. I really enjoyed the sort of first installment of the little sort of mini-series we're putting together here, where we explored the practicalities of interleaving in the primary math, or certainly in the mathematics classroom. And I thought this week we would explore one of your expert edit pieces, which gets to the heart of the debate on conceptual understanding versus procedural understanding, which is a bit of an ideologue's playground in my experience. And I really like that we're going to have the chance to get under the skin of this really important topic. So I think diving straight in, what do we know about the relationship between procedural knowledge and conceptual understanding, and how might this inform how we structure mathematics teaching?
Yeah, as you say, Kieran, there's been a lot of debate about this, and for a long time, I think there's a kind of seminal paper that some listeners might be familiar with by Richard Skemp from the 70s that sort of kicked all of this off. But thankfully, we've got some pretty good research on where we might want to be in this debate now, I think. But before I get into that, let's start with sort of a bit of definitions, what do we mean by procedural, and conceptual knowledge, and then also why people might disagree about how we structure maths teaching as a result. So procedural knowledge is kind of relatively straightforward. It's knowing how to do things, so following procedures. So for example, if you want to find the area of a right angled triangle, you'd multiply the kind of two perpendicular sides and then divide by 2. And that would be kind of your procedural knowledge. Conceptual understanding is a little bit trickier to pin down. It's about understanding concepts, but that's sort of a bit circular. But in the case of the triangle, that's kind of knowing what exactly we mean by area and what we mean by a triangle and all of those kind of things. And that's much more than just being able to recite a definition. It's about the connections between the ideas. We don't just conceptual understanding wouldn't just be that area is the space taken up by a 2D shape, but also what happens to area when you change the shape. Can you change the shape and keep the area the same? All those kind of things. So to go back to that triangle, the area of a triangle example, part of the conceptual understanding is seeing that the calculation, the procedure I spoke about, works because a right angled triangle is always half of a rectangle, and so that's why you're dividing by 2 in that calculation. Maybe it's worth thinking about conceptual understanding in terms of what it isn't as well. That can be kind of helpful. It's not doing things because that's the way they are, or because that's what someone said. If we ask a pupil to kind of explain a calculation and they say because you have to do it like that, or because my teacher told me, then I'd probably suggest they don't have too much conceptual understanding for that idea. And it's probably worth remembering these things are sort of a spectrum. It's not that you have conceptual understanding or not conceptual understanding. You can have deeper levels of that. And as going back to the kind of original question and your kind of lead in, there's a lot of debate about, or has been a lot of debate about the extent to which each of them are important, procedural and conceptual understanding. And some people might claim that maybe because of their own experience, that doing the maths is the important bit, and so the procedures are what matters, and that we just practice doing column addition or finding the area of a triangle until it's automatic or almost automatic, and only then, if at all, worry about understanding the concept. Whereas other people would say maths is about understanding, not just doing, and so people should be focusing on understanding why a procedure like column addition works before sort of teaching the process. As ever, like most people are in between those extremes. Like very few people actually sit at one of those ends. And the research, like particularly, there's a really great academic called Bethany Rittell-Johnson, who does lots of work into this. It's like kind of gives us a path sort of to navigate through this. And basically, what her research and research of others finds is that if we teach for like to build conceptual understanding, like making links between ideas and explaining why, that also helps pupils learn procedures better. And also teaching pupils how to do things, how to do procedures, reinforces their conceptual understanding and helps them learn concepts better. So it's win-win, really. Like the research is really quite clear that we should teach procedures and concepts. So like how to find the area of a triangle and why it works. Kind of, I don't know, 10, 15 years ago, there was we kind of knew that, but we weren't really sure about how we might balance that or where we might start. But actually, more recently, like Rittell-Johnson sort of suggests that we should have a kind of iterative approach, like moving backwards and forwards between conceptual and procedural understandings. They kind of get that chance to reinforce each other. So, like to give a different example, if we think about adding fractions with different denominators, we might start with like ideas of like things having to be the same for us to be able to add in, like the same kind of thing for us to be able to add and subtract them. And then some work in common denominators with like representations of fractions. Then we might move on to our kind of procedure for adding and subtracting fractions, like with a common denominator, and practice that and get good at it. And then come back again to the concept and sort of get people to explain why it works and make those links now that they've got that kind of set in their head. So like kind of going backwards and forwards like that is what the research suggests is the best option. Is one thing that's really not clear about from the research is where you should start, whether you should start with procedural or the conceptual. My like personal sense as a maths teacher is like it depends what you're teaching and the people you're teaching. And personally, I tend to want to start with the concept because I find it's easier to make connections and draw on pupils' existing knowledge. And also my experience tends to be that if I start with a procedure, that pupils get hung up on like getting it right rather than thinking about the maths. But there's definitely exceptions to that. Like if I was teaching dividing fractions, I might start with a procedure because it's kind of really complicated to understand why it works and not that hard to understand what's going on. And similarly, like way on with A level, like calculus, I tend to start with like how would you do for a differentiation rather than kind of complex limits and so on behind that. Overall, I think the research around this is really reassuring. Like teaching pupils conceptually as well as procedures, like not only improves their results, but also like it's kind of what makes them mathematicians, right? Like if you understand maths and you can experience that kind of power and beauty of maths, and not it's just being this like set of rules that you have to kind of churn out and learn by heart. So it's really nice that the research actually does back that up, because if we didn't, then we'd have to think perhaps again about where we put our efforts.
I think it's really helpful to explain these terms so we can all be really clear on what we mean when we say procedural and conceptual understanding. For me, I suppose these two forms of knowledge are really interconnected and mutually reinforcing. It is really great that we are talking about this and thinking about the relationship between procedural and conceptual to help inform the structure of mathematics. And when we are teaching people how to solve a mathematical problem, as John said, we don't just want pupils to memorize, we also want pupils to understand the underlying reasons why the procedure is effective. And so when they're faced with a similar problem, they can choose the appropriate strategy to help solve the problem. And I think this links really nicely when I was thinking about this, Kieran. I think it links really nicely to what I shared and what John and I shared in the previous podcast about interleaved practice. and how doing this can help pupils apply the knowledge they have learned in a different context. So I suppose our role in school is to support pupils' mathematical thinking and help them develop an understanding of the underlying concepts behind the procedures they are taught. And this enables them to transfer those procedures beyond the specific instructional context. And research suggests that pupils often struggle to develop conceptual understanding from a procedure, particularly when it is introduced using abstract mathematical symbols. However, since understanding and manipulating abstract symbols meaningfully is a critical aspect of learning mathematics, their use in instruction cannot and should not be avoided. And in a primary setting, I believe that the concrete and the abstract should go hand in hand, as we know that introducing abstract symbols during instruction can enhance people's ability to extend their knowledge beyond the taught procedure. I really like this paper, the Fife et al. Paper, because it focuses on primary age children, say 7 to 9 years old, making it especially relevant to me and my primary colleagues, and those people who are listening, who are sitting in a primary setting. And I think it also highlights the fantastic work that primary school teachers around the world are doing in their maths lessons. And as John said, I found it really reassuring. And sometimes it's really nice to have that reassurance to see that the concrete examples that we so often use in lessons, which then can be explicitly transitioned to abstract symbols, aligns with this, the concreteness fading technique explored in this study. In terms of how this might inform in the structure of mathematics teaching, this brings me to kind of the special place that is the early years. And in the early years, children often begin with conceptual insights. For example, understanding that addition involves combining quantities before developing procedural fluency. And as pupils move through their primary years, they start to encounter more advanced topics. And this is where procedures can sometimes precede conceptual understanding. For example, pupils may learn to solve simple equations by memorizing steps before fully grasping why the method works. And I think I said this in the previous podcast, but for me, it's about balance, and the balance between using concrete and abstract, which John and I will speak a bit more about later. And I think starting with instruction before introducing procedures may be beneficial in some areas, while in others, procedural familiarity may scaffold that deeper understanding. And then when we also think about assessment, we should ensure that pupils can not only perform calculations, but also really explain their reasoning.
What you've done there is sort of highlight the depth to which your expert edit goes in terms of making connections, because obviously we've got you've identified some really well-researched papers, because when I read the study, like the design study of this study, I thought this is fantastic again. And everything is working towards making teachers more effective in the classroom. But the fact that there's this relationship between the ideas that these researchers are exploring and the ideas that the previous group of researchers are exploring, it's almost like, you guys are playing 5D chess, and while I'm sitting here playing checkers in podcast world. That's the first thing that jumps out. And also the examples as well that you've chosen, because you can see that just like interleaving, there's a chance that many teachers are doing this as not a part of their practice. And what this paper does is then give them the confidence to really lean into that. But also, it shows the complexity, whether you're in primary or secondary, of when to make that decision. For instance, the objective learn number bonds to 10. That's like one sentence in whatever curriculum or like sort of document that you find it in. But we know that's a long journey in terms of both the understanding of what that means, but also at some point you need to commit those things to memory so that you can use them as you're developing understanding. And so whenever you're talking about the early years there, Emma, I'm thinking, I've already said we need our most skillful teachers there, but it actually almost amplifies that.
So the paper is called Benefits of Concreteness Fading for Children's Mathematics Understanding. It's by Fife, McNeil, and Borges or Borjas, I'm not so sure totally how you pronounce the last person's name. Again, a really catchy title, but it's essentially around, as Emma kind of spoke about there, moving between like concrete kind of physical representations through sort of pictorial towards abstract ones, and the kind of impact that can have on people's sort of maths learning.
So the study highlights the challenge of premature reliance on abstract symbols. How might teachers strike the right balance between concrete and abstract representations in their lessons?
Let's start by revisiting that word I mentioned earlier, balance. Like with most things, it's all about balance. Striking the right balance between concrete and abstract representations is really important to support pupils in developing their procedural fluency and conceptual understanding in mathematics. And as the study suggests, if abstract symbols are introduced too soon, pupils may struggle to grasp their meaning, while remaining at the concrete stage for too long may hinder their ability to analyse and apply knowledge flexibly. There is a lot of research about the CPA framework, the concrete, pictorial and abstract approach, which I am personally a big fan of. It gradually transitions pupils from the physical objects, so the concrete, to use drawings, the pictorial, to then abstract symbols. And often with my Year 6 pupils, who, in my opinion, sadly, don't always get the option for the concrete or the pictorial stages. And if they were struggling with solving a problem in the abstract, I would always encourage them to walk back through the CPA approach, that concrete pictorial, before they get to abstract. So I would say to them, could you draw it? Or could you get some apparatus or equipment to help them see it and to help them explain it before tackling the problem in the abstract? Now, this takes us back to the Jerome Bruner research about how CPA, concrete pictorial abstract, can scaffold learning. And he found that when pupils use the CPA approach as part of their mathematics education, they were able to build on each stage towards a greater mathematical understanding of the concepts being learned. Now, which in turn led to information and knowledge being internalised to a greater degree. And as we know, pupils achieve a much deeper understanding if they don't have to resort to that rote learning and are able to solve problems without having to memorise. So when we're teaching young children to read, we recognise that they need to have encountered a word to understand it. Simply putting together letters k, a, t would be meaningless if they had no concept of what a cat is or had never seen a picture of one. And I think the same principle applies to mathematics, though it is sometimes often overlooked. And for many children, mathematical concepts can feel just as abstract and meaningless without the support of concrete resources or those visual representations. And if we think about the concreteness fading technique from the paper, it involves systematically reducing reliance on concrete supports as pupils gain that understanding. So, for example, teachers could start with a real-world context. So, sharing pizzas for fractions. I think I've used Smarties in the past for teaching fractions of number, and gradually replacing kind of real objects with drawings or diagrams. And then finally introducing those symbols and notations, helping people see the kind of underlying structure.
Yeah, I think that kind of point you started with about balance is really important. So I might kind of look at the same idea from a different angle. Before I do, just briefly, I think you alluded to there's quite a lot of research around concrete, pictorial and abstract approach. But what I think is really great about this Fife et al. Paper is it goes beyond the theory and it really tests it out kind of empirically, which I think we spoke about last time can often be kind of lacking in the sort of subject specific research. It gets too caught up in only the theory, which is still important, but without actually testing it. So for, going back to kind of the purpose of concrete representation. So for me, that's about helping pupils understand the abstract symbols so that they can use it. The reason we've got those abstract symbols in maths is because they're efficient and they can be transferred to lots of different situations. But to do that requires that kind of conceptual understanding underneath it all. That's sort of what enables that to happen. And so the balancing of concrete and abstract and pictorial and sort of in the middle representations is about sort of connecting the two together. So if I want to like explain the concept of, explain kind of the column method for addition, I want people to understand what's going on when we regroup or carry or whatever we want to call it, ones into tens or tens into hundreds. And this is because I want the method to have meaning for pupils. Like, I think learning is about meaning. It's kind of just processes arbitrarily. There's no point to that. I want people to remember it, and like I want people to be able to like apply that knowledge. And as we kind of discussed before, the research suggests that like conceptual understanding helps with all of that, and then procedure helps people do better with the procedure, and then also being better with the procedure will sort of reinforce that conceptual understanding as well. So I could try just explaining what I'm doing. Like now I've got 14 ones, which is the same as 1 10 and 4 ones, and so I write a little 1 in the tens column. But for the pupils we're teaching this to, that's really abstract. It's really kind of like hard to like comprehend. So it's much better to kind of demonstrate it, and much easier to like understand if we demonstrate it with like a concrete manipulative like Dean's block. So for those like non-primary colleagues listening, those kind of like hundreds, tens and ones cubes that you'll have kind of experienced probably yourself when you were at school. And they're helpful because pupils can literally see that like equivalence and that change between ones and tens. Like going back to this kind of relationship between the two, like just demonstrating that on its own doesn't help. You kind of need to make the links between that and the written method and draw pupils' attention to like what we're writing for each of our actions. And that's kind of one of the things I'm thinking about when like balancing between concrete and abstract. And I think that's true all the way up to like I'm a secondary maths teacher, like as background, like it's true all the way up to A level. Like pupils have to learn like what happens to the mean and variance when we code statistics. I know this is a primary podcast. It's going to be a very brief diversion into A-level maths. And I don't want them just to teach them a rule. I want them to understand that like, if we've got some numbers and we add 20 to every number, every piece of data, then the mean will get larger. And so like I want them to think about like pupils to think about what's happening there. And so even my A-level students, I might get them to think about their mean height and then like stand on the chair and say what's happened to the mean height now, and like that might help them comprehend it because it grounds it in that specific context. But it's no use unless I like relate the general calculations and the kind of coding back to what we were doing earlier. So it's really like linking those two together, which is what this kind of paper is all about. The kind of fading between the concrete and the abstract is what makes like both of them more powerful, essentially. And then kind of maybe a last point, that the paper we're talking about is specifically about physical objects. It's like kind of what you call a manipulative. The authors do also acknowledge that like concrete doesn't have to mean physical. It can also just be something that's familiar. And like as an example, like the expression 3x is really abstract to most year 7 pupils. So like kind of representing using kind of counters or blocks or something to sort of represent that is likely to really help. But for an A-level student or a maths teacher, that idea of 3x is quite concrete. It's a thing that you can kind of imagine doing stuff to. And so the manipulatives might not be as necessary. And so that kind of concreteness goes beyond just the physical. It's the familiarity, and like teachers of other subjects will sort of be familiar with that as well, like kind of concrete examples of, I don't know, verbs, or like in history thinking about concrete examples of what monarchy looks like and things like that.
That's really interesting. It's actually something I was going to ask about as well, because Clements and Saran, I don't know if they coined it, but they talk about integrated concrete knowledge, which essentially is what's known to the pupils is concrete to them. And I go back to maybe Dan Willingham. He talks about that's that concreteness. Doesn't have to be physical and doesn't have to be sensory concrete knowledge. And obviously you've got the possibility of using like virtual manipulatives. Is that anything that's been on your radar as a result of reading this paper, or because almost like it's that the proponents of it would suggest it's one step further removed in terms of you can physically touch these manipulatives, but it's less of a touch. I don't know if that's the most accurate way to describe it, but it's almost like you're a further degree of separation between you and the resource that you're manipulating.
I'd be really interested in Emma's kind of early years perspective on this in a minute, but I think for me, reading the paper again, just sort of in preparation for the podcast, really made me think about this, because I've been thinking a lot, the last year or so, in terms of like concrete being familiar, and therefore not necessarily needing to be something that you can like touch, but actually like reading the paper made me think again about things like something around counting and there's something about the rearrangement of things. My guess is it is like the cop-out answer. It probably really depends on what you're doing. So I think, and the peoples you're working with. So work with kind of angles and circles, like circle theorems later on in like secondary education. You can use like interactive diagrams that you can manipulate, and I think they're really powerful there. And similarly, I've used like, I suppose, like bar models on an interactive whiteboard, and you can manipulate those to an extent. But I think it probably depends on what prior knowledge pupils are coming at this with, and what the content is that you're trying to like get to. Because I think something like, I don't know, maybe like square numbers or like factors and things like that, there might be something around like actually physically moving counters or like cubes around, so they create like rectangular arrays, or can't create rectangular arrays, and there might be like something to do with that. In summary, my cop-out answer is it depends, but I'm really interested in Emma's perspective on this.
Yeah, I agree. I think it kind of comes back to that balance again. There's a place for both, right? Seeing more and more like those visual representations on a screen, and for some children that could be really accessible, and their way of being able to explain their reasoning and be able to access the learning, and that's right for them. I think it comes back to the needs of the pupils, with kind of my former Senko hat on as well, and thinking about the Sen space. I think it's about what the pupils needs. But I think also for me, and we think about early years, and we think about our early, our most youngest of learners. I was going to say little then, but they're not always little, are they? Our youngest of learners, they need that one-to-one physical correspondence. Often, not always, but often, they will need to physically touch the block or little cube and move it. And that physical one-to-one correspondence, I don't know, but I imagine that you don't always get that same feeling of the physical kind of block and moving it into a different space, or being able to kind of do counting and balancing of equations, or as they move forward. And I suppose that manipulative word you can manipulate on a screen. Of course, you can. John's just rightly given us a concrete example of that. But I also feel in the younger years, there's definitely a place for that. I suppose it is that physical manipulation of some of these, getting to touch it, feel it, break it apart. If you're thinking about 10 again, yes, if you had a stick of 10 cubes on a screen, you can obviously separate them. But I think that the physical act of breaking them apart, and you've got 8 and 2 and all the different ways that you can break that stick of 10, I think is really, really vital. And I agree with John. I think it comes down to the content of the curriculum that you're trying to teach. And I think we talk a little bit about later on about there's a place for concrete materials, but there's also possibly a place for them not to be. And I've seen at times that teachers can sometimes use them not incorrectly, but in a way that can be quite confusing for children. So I think it's also just really thinking about the content of the curriculum and what's appropriate for the pupils and the needs of those pupils as well.
Yeah, I think just to kind of add to that last point, I think the question I'd probably always ask myself is like, how does this representation link to the mathematics and the structure of the mathematics behind it? I'm trying to think of things where I would really want to use a physical thing rather than an on-screen representation, and perhaps like one of those things might be like folding things in half for symmetry and things like that, rather than because that kind of like property is that it's exactly the same. But yeah, like what do people know? How does the representation link to the mathematics behind it?
I don't think it's a cop-out answer. I mean, before any early years teachers get in touch in my direct messages, in my mind, I'm thinking it's normally year 2. I'm thinking about having this conversation with teachers about, because they often say to me, "Oh, they can do it with the manipulatives, but they can't do it in their books," and it's almost like an extra step. I do agree, but I think you mentioned movement, John, with the arithmetic structures. Sometimes the only distinguishing feature between those contexts is the actual movement. If you think about augmentation and aggregation, it's very difficult to show that digitally. Even when I try to show teachers at, like, say, Research Ed or whatever, I'm thinking, I wish this animation was better, and sometimes you can get it to work, but it's much better if you've got the physical objects there in front of you. So I think you're on point. It's just, this is a conversation me and Chris Such started about 4 years ago, and we haven't really resolved where we fall on it. I just thought I'd test it out with you guys, as you've done such an amazing amount of reading on this subject. You actually mentioned mean, and this actually ties into the conversation my 2 boys were having about a month ago. Because my oldest 10 said his younger brother was playing cricket in school, and he asked him to help him understand the rules, because he had a maths question about cricket and he didn't understand the rules. Now, the question was a question of how many more runs would they need for the mean to rise to 17 from 10. And he was so distracted, and he's a decent mathematician, so distracted by the surface structure that, I mean, even when I was reading this paper, this conversation came to mind, but also, like, things about, like, the soldiers and the surgeon problem and the distraction. Is that sort of what we're trying to almost account for or alleviate? Is that distraction by surface, because we've got this this combination of the procedural and the conceptual allow us to go deeper into the mathematics, or am I making a leap there? But when I was reading this paper, those are the 2 things that jumped out of my mind. I remember he was having that conversation. I remember I've read this.
Yeah, I think that does link quite nicely. I think the kind of, I suppose, on the one hand, it's around sort of perhaps what Emma was sort of touching on, is that some of the research around concrete manipulatives can be a little bit mixed in terms of their impact, and it tends to be where the manipulatives, and I think we might talk about this a little bit more later on, but like where the manipulatives are distracting in themselves, because there's too much information going on in the manipulative. They're too exciting. I don't know, for example, like using football stickers as like as something to count. Like you're just going to get caught up in the football stickers, or I would be anyway. And then so I think there's maybe that kind of distraction element. I think the other point is perhaps just that, like, transfer is really hard, and I'm assuming that this is probably one of the first problems around mean that your son's come across. And also, if he's doing it at home, he's not just had the lesson on mean like 30 seconds beforehand. So he's had a chance to get kind of his attention drawn away from that. So it doesn't come to mind in the same way that, like, quite often as maths teachers, certainly at secondary, we'll do a lesson on like fractions, and then all the word problems are about fractions, strangely enough. So like pupils can kind of do them, and then they have a test where they have a word problem about fractions that's come after a column for the question, and they've got no idea what's going on. So there could be something around that. Yeah, I think all this stuff around, like, putting stuff in transfer is really hard, basically, not just for 10-year-olds, for human beings in general. Like, we find it really hard to apply things in new contexts that we haven't seen before. So I wonder if that's the kind of heart of it.
So there's sometimes disagreement about the use of concrete representations. We've sort of alluded to that a little bit. Whilst some claim they are helpful because they make abstract ideas easier to understand, others claim that pupils get too hung up on the initial context, just as we've mentioned, and then can't transfer their understanding to new situations. How does this paper fit into this?
I suppose before we look at kind of the strategies that teachers could use, let's just take a moment to kind of remind ourselves and your listeners and revisit the summary of the study. I think it's important just to kind of go back to the study. So the study compared how well children could transfer their knowledge to new situations after having received instruction with concrete representations, B, abstract representations, C, concreteness fading from concrete to abstract representations, or D, reverse fading from abstract to concrete. And in experiment 1, children in the concreteness fading condition solved more transfer problems correctly than children in the other conditions. So particularly interesting is that concreteness fading resulted in better transfer than abstract alone, even though the transfer problems were more similar to the abstract examples. Reversing the fading from abstract concrete was no better than the abstract and concrete conditions, eliminating various alternative explanations for the superiority of concreteness fading. The study involved a range of formats and contexts, indicating that the specific progression from concrete to abstract played a crucial role in influencing children's understanding of mathematical equivalence. And these results offer substantial support for the effectiveness of concreteness fading. And in the paper, so Fife et al. Conducted 2 other further experiments into concreteness fading, which I'll mention now, but we obviously don't go into the detail in the expert edit. We focus on experiment 1. But in experiment 2, the study addressed an alternative hypothesis by including a condition in which children played through the concrete and fading stages, kind of like warm them up for the abstract instruction. And then experiment 3 tested whether the benefits of concreteness fading extend to children with high prior knowledge. So the study confirms that children's understanding benefits when problems are presented with concrete materials that are faded into abstract representations. Extending our knowledge appropriately beyond an instructor procedure, as we've already mentioned, can be really quite difficult. It's really hard, as John said, to do this. And learners, and in the paper it says learners either fail to see that the procedure applies in a novel situation, or they readily transfer the procedure to the situation, but without adapting it appropriately. So if I give an example, before children receive instruction on maths equivalence problems, they often transfer in an incorrect add-all strategy from their experience with typical arithmetic problems. So for example, if you've got paper and pen ready, you might want to make a little jotting down as I go through this little example. So we've got 3 plus 7 equals, and then a blank. So that kind of balance of equivalence problems. So when the pupils are given this, with this, adding all of those is a strategy that works really successfully. But even after children receive instruction, correct transfer is often limited to problems similar to those presented during instruction. So for example, in the study, when children were presented with, get your pen ready, 3 plus 4 plus 5 equals 3 plus and then blank, they're taught to cancel the 2 3s and add 4 and 5 to get 9. They subsequently then solve, pen ready, 6 plus 3 plus 7 equals 6 plus and then blank. So correctly, by adding that 3 and 7, but they also add 3 and 7 when presented with final one, 6 plus 3 plus 7 equals 4 plus and then blank for them to fill in. So similarly, in the study, all children learn how to apply a correct procedure to solve a specific type of maths equivalence problem after explicit instruction and feedback. However, most children had difficulty applying and adapting the procedure to novel problem types. Importantly, concreteness fading resulted in superior performance relative to other conditions and reduced children's incorrect transfer of the add-all strategy. So these results suggest that fading technique helped children extract better understanding of the underlying concept from the instructed procedure. And the benefits of concreteness fading can be explained by the fact that it starts with a really well understood concrete format and explicitly links and fades it into the abstract symbols. So concrete materials are advantageous initially because they allow the maths concept to be like really grounded in easily understood, like real world kind of scenarios, I suppose. And I think the next bit about the strategies that I wanted to kind of think about, I thought of kind of 3 strategies that I would kind of suggest to teachers. Is kind of like start with those concrete resources when they kind of help pupils understand the concept. I know we've spoken a bit about making sure that, you know, they're not too distracting, because it, you know, it can, you know, distract our attention away from actually what we're trying to learn and what we're trying to focus on. Primary, you know, or secondary, if you're listening to this, you know, you can help pupils grasp mathematical concepts more effectively by thinking about the right concrete materials, and then gradually moving to those pictorial representations such as bar models to kind of like bridge that gap between the concrete and the abstract thinking. And I suppose as you kind of like transition to abstract symbols, like reinforcing all the time those connections to both pictorial and concrete representations, encouraging pupils to switch between those representations as well, kind of that fluid back and forth, as this can really help deepen their understanding. And then like often using visuals or concrete resources kind of like prompts that explanation piece, which I think is like really, really valuable. And that leads on to my 3rd point. But my 2nd point is to represent concepts in kind of like multiple ways, to prevent pupils from associating them with just one context. So, for example, fractions can be shown as parts of shapes, points on a number line, a set of objects, and kind of like using varied problem types to help generalize their understanding, asking questions. What is the same? What's different? Can really help encourage pupils to identify the kind of like underlying mathematical structures. And then my 3rd one, which I've kind of touched on, which is that encourage that reasoning at every opportunity. So whether that's verbally or in writing, obviously depending on the needs of the children and the pupils, asking those what if questions. What if the number was bigger? To promote that flexible thinking. And one of my favourite strategies I've used is kind of prove it. So what? Prove it. Prompting them to justify their answers in multiple ways and just help them deepen their kind of mathematical reasoning.
Yeah, I love that point about encouraging reasoning and like what if questions. But I tend to sound a bit like a 5-year-old when I'm teaching maths, because I'm just constantly asking why. Like, yeah, I think we've covered lots of the points there. Like the most important part of the study for me is that like fading from concrete to abstract. It's not like that you are using concrete or not using concrete. It's that kind of transition between the two. Those concrete representations, so in the paper there's kind of like balance scales and things like that, like are easy to make sense of because they're familiar to pupils, but they're unhelpful because they're like tied to a specific context, and actually we want equations and things to work beyond ideas of just balance scales. But on the other hand, like we've got abstract symbols, and they're hard to make sense of because they're like unfamiliar and abstract. But they're helpful because they're not tied to that specific context, and that's kind of like what makes maths powerful, right? You can use it across so many different situations. But fading between those two like means we get the benefits of both. Like we can use the concrete examples to kind of help people to understand, and then the abstract like help them apply it efficiently. But we have to make those links explicit to the pupils we're teaching. So if I was, I don't know, teaching like surface area, I might unfold the net of a 3D shape. But I need to make sure that pupils then like are really clear that that area of that net is the same as the area of the surface of the surfaces of the shape. I need to avoid like any little tabs and things like that on my net, because that'll confuse them. In this case, it's very helpful for building my net, but not for calculating the area. I might need to kind of keep unfolding and refolding to sort of draw attention to that. And I also need pupils to be able to like make the link between seeing the shape in front of them and in 3D and the kind of measurements on it, and where those measurements will be on the shape. And like they're going to find that difficult because it's new to them. I've got to draw attention to them and say, look, right, you can see this fold here, this line here, that's going to be the same as this bit here, so it's going to be the same length and things like that. The same is true of kind of pictorial representations, which can be that kind of bridge between concrete and abstract. If I'm using a bar model, like I will like to represent an equation, I'll have the algebraic equation to the side, so I can say, right, okay, well, if I'm going to remove these things from the bar model, that's going to be the same as if I subtract from both sides of my equation, and also that if I only remove from one side, it's no longer equal, so I have to remove from both sides. If I teach people using a bar model, and I go to a new slide and I teach them with the symbols without explaining the link between the two, I may as well not have bothered with the bar model. I could have saved myself some time. So it's all about that kind of linking, that fading together. And I think going back to Emma's other point about sort of multiple representations, I think that like using lots of representations to kind of understand a concept can be really helpful, like seeing what the fraction can look like kind of discrete objects with shaded parts of a shape with a number line really helps build that broadness of understanding of the concept. But if we want to use a representation as a kind of tool for solving problems, like whether that's a number line or a like graph or like helping represent things with the bar model, we have to teach people how to use that representation and the links between it and the abstract symbols. Like the classic thing that as you teach people as they get older is that like if we understand the graphs of equations, it makes equations way easier to solve. We learn loads of other stuff about them that we can't do just from the algebra. But often people find graphs a hindrance and not help because we don't really teach them those links for it, like as well as we could do, because it's hard, it's difficult for people to get. And I think the last point the question was sort of around strategy for transfer. I think Emma's given us lots of good ideas there, and we said earlier, like transfer is really hard. The kind of research more generally outside of math suggests that like plenty of practice helps. Like introducing those kind of things that like Bjork and Bjork called desirable difficulties. So like interleaving, like we talked about last time, like mixing up the questions, getting them to retrieve learning regularly to help them strengthen that memory. And then I think perhaps the thing that links most to what we're talking about today is that kind of like self-explanation or elaboration, explaining like why they know they're correct or like how they know to do that next step. And I think we might come on to that as well when we talk about one of the other papers in the expert edit in future. But I think like it's all about what is it you wanted people to think about. That's the kind of big question.
I think that's going to be really, really important for a lot of listeners, because one of the things I'm struck by when I'm speaking to teachers in England is that they're stuck on a conveyor belt curriculum, and the resources they've got almost, in their words, bombard the pupils with representations. And that's not necessarily what we're talking about here. It's very much there is a relationship between each step in that feeding, so that the carefully chosen representations, like you mentioned in point 2, Emma, they feed into that journey for the pupils. I mean, have you guys seen? I mean, have you seen that? But you know, from my perspective, this year in particular, I've been asked it a lot, and I just sort of almost putting two pieces of a separate puzzle together there when you guys are doing, because I think your sort of responses perfectly complemented each other in terms of here's what we can do and here's how carefully we should think about it.
It's very complex, and I think you make a good point, John, around it's not multiple different representations of lots of different things can be really, again, another distraction for people. Just like if you say, oh, you've got all of these different strategies, and I think that's where I was coming to around then people's, when they're trying to select the right strategy, are so confused, so overwhelmed, that cognitive load is just too much, and they don't, because there's too many representations. I think we're talking about that, connecting the representations within maybe one concept,
choosing the right, like kind of a good representation for the purpose. I think at secondary, my experience is probably it's more often at secondary that teachers don't use representations as much as they could do. And that might be, I don't know, the classic example is where all the rectangles you ever draw on as a teacher, you ever draw on a whiteboard are all like that. They're never a kind of angle, and they're never squares and things like that. Or actually, just not really making use of things that could help. Like, I don't guess, I didn't learn about bar modeling until I'd been teaching for quite a long time, like a good 7 or 8 years or something. And actually, I suppose that's what I come back to, because it's really versatile. You can use it for ratio, you can use it for fractions, you can use it for like basic number problems, you can use it for quite difficult algebra. It leads on to like you can make connections with other things like people might be familiar with sort of algebra tiles, which are really versatile. That teaching, like picking a couple of things that work well for the context, is better than like just throwing representations at it. Like you don't really want to be using Dean's blocks for angles, like that kind of thing, like avoiding that.
Yeah, I was just going to add to say, resurrect those Cuisinart rods. I did a piece with Greenwich University, and it absolutely, but it definitely changed my thinking around the introduction and use of like bar modelling, and that's kind of links to your question, Kieran, about like on the screen bar modelling has a place. It really does when you're showing the relationship, having the physical kind of Cuisinart rods on the tables for pupils as well to manipulate. And they're so versatile. I've used them, when you say like this Cuisinart rod is worth 50, and and every rod can obviously be 1 to 10. It can be they can represent any number. It can link to decimals and percentages, and it's amazing. So check it out on Cuisinart rods.
Yeah, they're very much the I think they require the biggest investment of all the manipulatives out there, but once you've got them, so powerful. I mean, I think I spent the best part of 3 years with DMAT just looking at that with their subject leaders, and they were flying at the end of it. But we started off building faces with a value of 100, etc., and worked our way up from there. Was it the Christmas trees and stuff like that there? And then
I think we did building trains.
Yeah, trains, yeah.
Make a train.
For all of you Kofi, Ko-Fi, Ko-Fu-Fu, however you pronounce it, you damn lovely supporters. It's a song going out to you, to you. Okay, here we go. Nikki Anna P. Septi, Stephanie Taylor, Mrs. B. Esatea, Adam, Katie, Liv Dempsey, Becca, Jenford, Susie Brown, and Cio, Netchio, Rachel, I am Al, Jessica, Tom Oakley, Tom Brassington, Jessica, Tom Oakley, Tom Brassington, LJ, and last but not least, my lovely little Amy Bill. So they help us pay the bills. So a massive thank you out to Dappe family. Coffee supporters help us keeping it ad-free. There's far more content coming just round the bend. Thank you all for helping our very special friends. Very special friends.
What are the key implications of this research for teacher professional development, particularly in supporting educators to implement concreteness feeding effectively?
There's probably a couple of things in terms of teacher professional development. I think firstly, like teaching, this is all going to get quite meta. My wife's favorite thing is describing me as someone who teaches teachers to teach teachers, etc. But I think in terms of like teaching teachers how to do concreteness fading is probably like quite similar to any like sort of supporting them with any other aspect of pedagogy. I'd lean pretty heavily on the kind of Sims et al. Paper on mechanisms of professional development. So like providing teachers with really clear examples of what concrete and abstract representations are and are not, and like modeling like what fading between them might look like. So I guess going back to that kind of bar models and equations example, like showing them with them together and showing them on different sides and things like that. And then making sure teachers have got like time to make sense of those representations is what like those models and kind of explanations as well, like having like time to discuss it and like get their heads around it and ask questions and like not just presenting it to them. I think it's probably going to be helpful to use it in the context of the teacher's pupils. So this paper is very like grounded in like young children. So if I was working with teachers of kind of upper primary pupils or like secondary pupils, I'd probably choose some different examples, like maybe around like column addition or like fractions or something like that, some algebra. again, like back to the kind of mechanisms piece from the Sims et al. Paper, like providing time for teachers to practice, like perhaps scripting their explanations, or kind of as you just talked about with quiz and error, to like actually like playing around with representations. Because if you're a teacher, like you can't unless you can use the kind of manipulatives yourself or the representations yourself, it's going to be very, very hard to learn to do them. Like as a like extreme example, I worked for Maths Mastery maybe nearly 10 years ago now, and that was sort of where I first came across bar modeling, and I spent, I don't know, about 6 months where I'd try and solve every problem with the bar model first and then go back and compare it to my original solution. So like that really helped me get my head, the point there is it really helped me get my head around using it, and I was much better placed to support other people using it as well. And yeah, I think so the practice, like using representations, scripting your explanations, and then over time probably moving towards selecting which representation to use when. I probably would scaffold that to start with. I'd probably say, right, today we're going to like focus on using like a number line, or we're going to focus using on like a bead string or something like that, and later get teachers to think about, okay, like which one am I going to use when, and then have some follow-up to the sessions, like maybe some paired observations and feedback, or something like that. And it'll take a while. Like if teachers are not used to using representations or not used to fading between them, it's going to take like everything for all of us to learn things like that. Like it's going to take time to become proficient. So I'd take like time introducing it, which then gives you the chance to sort of retreat between sessions and things like that. So last time we talked about whatever we talked about and kind of ask some questions around that. And then I suppose there's probably like a pitfall I would really stress, which I think we touched on earlier. Like in general, the research into concrete representations, concrete manipulatives tends to suggest they're more effective if they're less realistic, like counters to represent football stickers, like sweets rather than kind of actual football stickers or kind of actual sweets in general. And like the fewer surface features, the probably better. Like a drawing representing pizzas or fractions is probably like you just want enough to tell it's a pizza, not like a really like tasty looking photo of a pizza, because I mean then I'm going to be thinking about pizza rather than like cutting it up into fractions. And that's slightly different to this Fife et al. Paper we're talking about. Like they did use like kind of puppets, which are quite enticing representations, but they seem to be quite successful. My guess is that like that worked this time because the pupils were really young, and so they needed that kind of very, very concrete like intro. But in general, I'd try and steer away from kind of really detailed concrete manipulatives. So just try and be like enough there. Yeah, so if people haven't read that like EF professional development guidance based on the Sims et al. Paper, like I'd really recommend that they do. And then the second thing I'd probably talk about, like kind of think about, is much more tentative. Like we know that like teacher learning is just kind of learning. Like if we don't know very much about something, we benefit from lots of like support and instruction and practice. So I might try and like fade the examples I used when I was working with teachers within the professional development. So it's unlikely we'd be like having manipulatives to represent like things that they were doing in the classroom. That's probably several steps too far. But I might show like, I don't know, a video or like a model of some concreteness fading in the classroom, and then highlight the like aspects I felt were important. And over time, we might sort of like as a group, like summarize what were the important bits about that. So you're going from here's a specific example to here's a more abstract summary, and like that we've kind of drawn out of that, rather than like here are the steps that you do to use concreteness fading in example, like starting with the concrete and moving to that kind of abstract point.
Being a former primary school teacher, I'm a huge fan of the puppets, I have to say, and the pizza. But I completely understand that point. And yeah, there are times, as I said before, a balance. Sometimes you need the puppets, and sometimes that's the connection our pupils have with, you know, many things. This is how we brush our teeth. The puppet's gonna, you know, we could go on. But yeah, I think just understanding that there's other research out there that I've actually picked up on recently, and John said about the kind of concrete materials can be a real distraction, and that's something that I've actually just been thinking a bit more as we kind of prepared for this podcast. That they might not always be helpful, So yeah, I think that would be the first thing for me when thinking about kind of professional development, would be exactly this idea of when and when not to use those concrete materials. The research kind of suggested it is not simply the inclusion of concrete materials in classroom activities that will enhance people learning, but the manner in which teachers employ them to illustrate or model mathematical concepts. To use them effectively, I think the teacher needs to understand the concepts we've said before, and more importantly, have that opportunity to play. And that's, going back to the Cuisinart rod example, that space to just play with them myself and understand. If you're looking at any new technology, sometimes the best way to learn is to just have a go yourself and explore. And I think, remembering to do that with our pupils as well. So yeah, to use them effectively, the teacher kind of needs to really understand those concepts, and more importantly, have the necessary pedagogical kind of content knowledge in order to maximise the likelihood of pupils understanding the new concept. And then, as John said, I think professional development needs to have space to explore what concreteness fading is and is not, with examples from the curriculum that teachers are planning from, to help them kind of build that knowledge around mathematical concepts. So this is really linked to kind of the mechanisms of professional development, as John's mentioned. So build that knowledge around mathematical concepts and strategies, motivate staff, motivate teachers, motivate them by kind of sharing the impact of concreteness fading. Is always that why are we doing this? Why is this important? Why is this going to help my pupils? So kind of that motivation piece of explaining the impact of concreteness fading, help teachers kind of develop those techniques, and then working on embedding the concreteness fading into practice. I suppose as well, to kind of support educators in implementing concreteness fading effectively. As John said, it takes time. It's essential to view this as a process, as a kind of structured journey. And I will refer to Sharples et al. 2024, a very great paper, just all about implementation. Go check it out. 4 key phrases and phases of implementation that explore, prepare, deliver, and sustain. So applying this framework can help schools develop a systematic approach to embedding concreteness fading in teaching and learning. So I've taken those 4 areas, and I wanted to kind of just think about the explore phase first, and kind of identifying and evaluating the concrete manipulatives that best support the teaching of different concepts across the primary phase, as an example. One way I thought about this is we could do this collaboratively, so within the early years, Key Stage 1, Key Stage 2 teams, and then kind of followed up by a whole staff discussion. And by sharing, insights, teachers can ensure that consistency and continuity in how manipulatives are used across year groups and to support people learning. So giving them time to explore. And if we move to the prepare phase, think about developing a strategic whole school approach to scaffolding the transition from concrete to abstract representations. This might involve establishing a clear progression model that supports pupils as they move from that kind of physical manipulative to pictorial representations, and then ultimately abstract symbols. And then in the deliver phase, I was thinking about kind of strengthening the role of the teacher in the process and how they deliver this. So, research indicates that greater teacher guidance leads to higher achievement. So professional development, could focus on supporting staff in delivering explicit instruction, that effective questioning techniques, modelling problem-solving strategies to help pupils make those meaningful connections between concrete and abstract representations. And then the 4th and the final kind of stage in the implementation cycle is that sustain. So ensuring that long-term success of concreteness fading by prioritising ongoing professional development. Teachers need strategies to help pupils generalise their understanding beyond manipulatives and apply their learning to new problems. And I think schools should, support educators in adapting concreteness fading to individual pupil needs. It comes back to that. What is it that my pupils need in this moment? And obviously that can change, as we know, day to day, hour to hour for some. Recognizing that some learners may require extended time with concrete representations. They might need much longer in that kind of explore phase if we're thinking about the implementation cycle, allowing them to explore the concrete representations, and others might transition more quickly. So I suppose in summary for me, to kind of implement concreteness fading effectively, teacher professional development should focus on selecting the manipulatives, structured transitions between concrete and abstract, teacher-guided instruction, problem-solving extensions, and adaptive teaching strategies. And by embedding, these elements, manipulatives kind of become a bridge to abstract understanding rather than a crutch, and ultimately enhancing pupil achievement and that conceptual mastery.
I think they're both fantastic answers. Again, another 5D chess example, because you guys have really thought very, very carefully about this. I mean, as far as I can tell, Jonathan Sharples has been quoted in every passing grade MPQ that we've had so far, and that's possibly down to the good work and ambition. But one of the things, you mentioned the mixed bag of research, where sometimes manipulatives don't seem to be that, and this goes way back to the 60s. Because, like I said, following that not argument, but that intellectual conversation with Chris Such, I did a deep dive, and I think that every decade between 1960 and 1992. So every decade in that 4 sort of decade window, someone said, we think manipulatives are a good tool, but we just don't have enough sort of institutional knowledge on the ground to get the most from them. And we need to spend some time thinking about how we can get the most from them. And then seeing that happen every 10 years and nothing happen, I'm thinking, well, at some point this has to change. And I think the conversation we've had hopefully can contribute to that, because it shows you both the shades of nuance, but also the things broader than what will this manipulative do that can help us in our professional development, because if we're thinking about the tool, it doesn't necessarily matter if you choose the right one, I don't think, because you can reflect on that and then get better at it next time, which I think is a lot of what teaching is. So I think, immensely useful for teachers, both in terms of the discussion about what this paper was saying and what that means for our practice, but also if we're school leaders and we're looking at development across a broader range of teachers, a really sensible way of thinking about it. So thank you very much, guys.
I might add, one thing. I think just reflecting on both of our answers to the kind of professional development point. We've both taken kind of quite a high level standpoint, and I actually wonder if, like, from an individual teacher point of view, or someone wanting just to get things started, I think perhaps it's about picking one or two manipulatives or representations. So I'd be interested in your thoughts in terms of both of you, in terms of like primary expertise. But my sense, if I was only going to use one manipulative, despite all the benefits of quiz and error rods, they're quite tricky. I'd probably use Dean's blocks. I think they're really versatile and actually really easy to get your heads around. And then I'd probably go for something like bar modeling as a pictorial representation, because it works as a really nice scaffold for number lines, which pupils often find quite difficult to use a number line well, whereas you can kind of have that bar model overlaid over the number line. But just picking one or two and trying that, and asking that question, what is this showing, and how can I help pupils to understand what this is showing? I think that's probably the other thing I would add.
And I think it's good to kind of remind ourselves of, not only as the listeners and thinking about their kind of realm of influence and the decisions that they can make today, tomorrow, that can have an impact on their teaching, but also their pupils. I suppose firstly I would look at what resources you've got. Look in your classroom, look in some cupboards that may have not been opened for a little while, and see what you've got in your school and your setting first. And then I agree, bar modelling is a good one. I think any blocks, little cue blocks, it doesn't have to be, they don't have to be multi-link, perfectly connected. They don't have to be Dean's blocks. I just think any kind of any kind of blocks that would kind of be a representation would be good. The bar modeling representation, I think, is superb. Other kind of drawings that, again, that pupils may be able to use. They might have a strategy, they might have a pictorial representation that works really well for them, and kind of exploring what our pupils know and can do as well. And I think the third thing I was thinking was, look at the curriculum. Next time you're planning, what's the content? What are my lessons going to be? What do they look like? And what resources could I use? Just as John's rightly said, choose one and explore that as far as it could go. It's not going to work for all areas of our maths curriculum, but it could work for many more that you might have not realised it yet. But just take a moment to kind of look at what you're planning next half term. What's the maths curriculum look like for you, and what concrete representations could you use to support your pupils with the concreteness fading into abstract?
Yeah, I think that's excellent advice all round. I think the choice of base 10 equipment brings up an interesting consideration for teachers, because I think I would classify it as a pre-structured resource, whereas like the cubes you're talking about, Emma, are unstructured, and I think you possibly get more bang for your buck in terms of the things you can do with it. But it is still important for teachers to think about that, and the fact that, what is magnitude? What is this describing here? So absolutely, I think that's, and I think maybe getting 6 weeks ahead of yourself and thinking, okay, after Easter, what am I teaching? And then that gives you the breathing space to think about that. I mean, it might work in real time, but I know that once the term starts, you almost get ahead of yourself, don't you? And then, or behind yourself, and you're catching your tail for the whole thing. So, but I think, yeah, on both levels, I think that's fantastic advice. It's been lovely chatting through this with you. And I think we've got one more at least on the horizon. All that's left to do is say thank you very much for joining me. Thank you very much, Emma.
Thank you, Kieran. I've really enjoyed this conversation. So thank you for having me, and thank you for having John and I.
Thank you, John.
Thanks, Kieran. Great to be with you again.
And everyone at home, until next time, thanks for listening.